a single argument that I'm interested in, which, like any good arguments, takes many forms, right? So it's been around for a while, people have said various things about it, I've said various things about it, and I want to introduce you to the argument because I think it's a really great one. Okay, so this is what I want to talk through today. I want to talk you through a couple of examples, and they're supposed to kind of get you into the spirit of the thing. So one is about honeybees and the honeycomb conjecture. The other one is about cicadas, which have prime life cycles. I'll explain each of those white terms. Hopefully you know what a bee is, and a cicada is just another type of insect. So the white terms will be explained over it. We're going to look at Alan Baker's enhanced indispensability argument. That's the argument I'm interested in. I've written about the unenhanced version before, and now he's got this other enhanced version. I've also kind of written about that. But yeah, okay, so we'll look at that. I want to bring up two of the things. So his argument is an argument for a position called Platonism about mathematical objects. And his argument hinges on a notion of parity, so I'll introduce what I mean by that. And then, I can't remember whether I updated this slide when I wrote the rest. Yeah, no, that's right, I'm going to talk about underdetermination, which is a key issue in the philosophy of science, and kind of relates to all of this. I'm going to try and draw something of a fairly weak conclusion about all of this. So even if my conclusion doesn't float, right, even if it's a terrible conclusion, which it may well be, because it's quite a weak one, you will have heard some cool stuff about bees, and about an argument that is really cool, and about Platonism, and about underdetermination. And that will be a massive achievement, because that will give us loads to talk about, all of that, in fact. Good, yeah, right, so that's a pun, it doesn't matter. Let's talk about bees. So back in the day, we get these kind of statements coming from people like Charles Darwin. We hear from mathematicians that bees have practically solved a recondite, I mean it's kind of difficult or hard to solve, problem, and have made their cells of the proper shape to hold the greatest possible amount of honey with the least possible consumption of precious wax in their construction. Bees have solved a problem. They have tried this. The problem they've solved is how do you get the largest surfaced area, what shape would you need, largest surfaced area, with the least expenditure of wax in making that perimeter. So yeah, the problem is how do you get a larger surface over the smallest perimeter. And bees have solved it, at least practically solved it. They've come up with a shape that works. And that went the wrong way. He says, notice that this is a biological explanation. He gives the motive power of the process of natural selection having been economy of wax. The individual swarm that wasted least honey in the secretion of wax has succeeded best. So one reason then why we might think that bees have hexagonal honeycombs is that it's most efficient for them, right? They'll succeed better. So it's kind of biological explanation or an evolutionary explanation. So why is it that, how is it that bees solved it, given that we don't think they're actually mathematicians sitting down trying to calculate these areas? But it's a kind of product of evolution, of natural selection, that if you're more efficient than your conspecifics and the things that you're competing with, then you're the ones that are going to stick around. So if you and me were both bees and it was like a kind of fight to see who could make the best hive in the shortest amount of time in the most efficient manner, then I would win if I was making hexagons and you were making octagons, for example. I'd be the winner, you'd be the loser. And I would survive, I'd have more sex, my offspring would go on to future generations, and hopefully my hexagon building ability would go into fixation. If someone was more efficient, and fixation meaning that they outnumber all the others until there are no others, right? If there was a more efficient way of doing it, then I would lose the battle, right? And I would stop being an efficient bee and I'd be a dead bee. So he's given a biological explanation of why bees make hexagons. Just to kind of, it's the most efficient shape, and efficiency is a really key consideration. Optimality is a key consideration in biology. Right. Actually, this view goes back a lot further. When we look in 36 BC, Varro, writing on agriculture, says, "Does not the chamber in the comb have 6 angles? The geometricians, mathematicians, have proven that this hexagon inscribed in a circular figure encloses the greatest amount of space." So right there he's saying, let's not worry quite so much about the biological explanation here. Is this actually true that hexagons encompass the most efficient area of space? And he's talking about within a circle, it's a slightly different issue. But he's already relating that to bees. He's like, there's something really cool about what bees are doing here, and it's something that mathematicians can prove. So he claimed that back in 36 BC that mathematicians and geometricians had proved it, and they hadn't. He's wrong about that. So a little bit later, 1743, Maclaurin, one of the people who was writing about the stuff, on the basis of the cells wherein the bees deposit their honey. This was passed for maths back in the day, so great title. The sagacity of the bees in making their cells of a hexagonal form has been admired of old, true, you've seen that above. The cells, by being hexagonal, are the most capacious in proportion to their surface. That's also slightly false, because there we're talking about an area, and really the mathematical problem at stake is really just the sort of two-dimensional shape, which is the area of a hexagon, where he's talking about the capacity of the cells. And when people start moving into the third dimension, where how much honey can it actually hold, the most efficient shape isn't going to be just like hexagonal in all shapes. It's going to be like a sort of squashed octahedron or octagon. But it doesn't matter. These people are interested in what's going on with bees. Bees make hexagons, and that would seem to be the most efficient. But is it really the most efficient? An interesting mathematical question. Is it true that a hexagon is the best way to get the largest surface area for the shortest perimeter? Everybody just thinks, yeah, well it is, and that's kind of why bees are winning in the battle of, the hexagon-making bees are more, plentiferous than the ones that are made, pentagons, because there aren't any of those, they all died out, right? So we can think there's obviously something correct about hexagons because bees are surviving. But it took until 2000 until someone had a proof of the honeycomb conjecture, which had been around for centuries, right? Been around since before 0 CE, and it took until 2000 until Hales gave a proof of the honeycomb conjecture. He's a real mathematician doing real maths. That the optimal tiling of a plane, by optimal we mean a minimal side length for the area of the tiles, is a hexagon. He gave a proof, and you could look it up. It's interesting. It has loads of cool shapes and maths and symbols on it. Real maths, right? Not kind of cartoon maths, but real maths. He points out in his introduction that previous attempts at solving it, most of which were kind of in the 40s, didn't work. You had to make special assumptions, like there's an assumption called the convexity hypothesis. He didn't use any of those. His was seen as a proof that was quite advanced because he was able to drop some maybe unproven assumptions. He doesn't involve that. He used some of the stuff that's going on in bubble theory. That's what mathematicians get to do. We get to sit around thinking about bees, and they also get to sit around thinking about bees, but they also think about foams and bubbles and those sort of things. So what shape would a bubble take if you just blew one bubble into, you've got some like soapy water and you put a straw in and you blow one bubble, it makes a circle. And what would it do to make two bubbles, if there was a sort of division in there? Would it be a circle in two hemispheres? And as you sort of keep going through that, do they start becoming square? No, but they start having interesting kind of convexivities around the side, and then bubble theory is really interesting. That's sort of an area of interesting maths. So he's using some really interesting maths going on there. His proof is long and looks very mathematical in all the right ways. So what we know then is that we have this kind of quite well-established biological explanation of bees, hive-building activities, or comb-building activities, which is they must be the most efficient, and that's why they've survived and are able to keep doing it. Then it's only until 2000 that we get a proof that that is the most efficient way of tiling a plane. So it's almost like that note that the biologists were writing, well, it must be the most efficient. That check was only really cashed when we got the mathematical proof. Up until then it was a kind of conjecture. Well, why would it be hexagonal? Well, I guess it must be the most efficient. Otherwise they would have died out because some more efficient bee could have beaten them. And then finally we get a proof, yeah, it is the most efficient. So good news. That's just one example I want to talk to you about a role that maths can play in real physical systems and real science. Right? So that's just one example. Let's move on to another example. So the North American cicada. I didn't put a picture on here. They are horrendous, right? And some people who live in areas of North America have to live with them, which is kind of horrible. So the North American cicada is a big. This example is given by this guy Alan Baker in several of his papers, and it's a great example, which is why I really want to tell you about it. I just think it's really exciting. Okay, so yeah. they're a bug. Some people call them locusts. They're not really locusts, but they're big. They have really big. They look sticky. They've got huge eyes. They're kind of, insecty but large. When they have little, when they make larvae, right, or nymphs or whatever, the small bug-like bit before they kind of grow into the fully grown cicada, that's buried in the ground underneath trees and it stays there for years. And then what happens is, all of a sudden, 13 or 17 years later, they come up as fully grown cicadas, and they climb up the tree. And they all appear all at once. So there are towns in areas of America where there are famous broods of cicadas. The most famous one is called Brood X, but I can't remember where it is. I was trying to remember this earlier. You can look it up on YouTube. There's video footage of Brood X. Because every 13 years it surfaces, and it's massive. There's just millions of these things. They all come up all at once within a couple of days. And they fly around, and they mate rapidly with anything they can. And their whole objective, once mating, is to try and bump into a tree, where they'll knock themselves out or something and fall down at the base of the tree, and the larva can then go back into the roots of the tree and start all over again. Which means during that 2-week period, not only are these incredibly noisy and very vicious and ugly looking bugs, but they're not vicious, they look vicious, sort of flying around everywhere, making this incredible racket, because they have these sort of huge wings that they rub together. And it keeps people awake and all that kind of stuff, they really go for it. But they're also intent on bumping into things. So you're kind of in a village where you're just being smashed around. Do you have villages in America? You're in a town where they're trying to bump into you. So it's kind of horrific, right? And Brood X is one of the most famous ones because it's just so large. These people get inundated with them. You can go out with shotguns. The interesting thing here, right, is the broods are only in the 13 or 17 years in that larval period. And it's only ever one or the other, depending on what actual climatical variables and the actual species they are. But it's always 13 or 17. Never less, never more. And that's kind of interesting. Why 13 or 17? And particularly, why prime numbers, right? Why would they be prime numbers? You might have noticed that they're prime numbers, right? So why are they prime numbers? And the sort of biological explanation that people put forward is, well, it allows them to avoid predators. If your predator has a life cycle that's, say, 2 years, then your intersection with them is sort of nicely avoided. The likelihood of avoiding them is pretty good. If it's 3 years, it's pretty good. If it's 4 years, it's pretty good. Whatever, depends. Similarly, another explanation is it allows you to avoid hybridizing with a similar subspecies where you might end up sort of watering down your stock. You know, what makes you into a good North American cicada might well be a product of this life cycle, this 13 or 17, this prime life cycle. And so if you start hybridizing with another species, a conspecific or a similar subspecies that doesn't have the same life cycle, then you're going to be changing your effectiveness. So there will be something very effective about having a 13 or 17 year life cycle. And so both of those explanations, whichever you prefer, and I guess people in biology kind of argue about them, but they have the same number theoretical idea. The thing at root that's good about both explanations, what makes them look like a good explanation, is that they say, well, if you have two things with the lowest common multiples, you want to avoid, so you want to avoid, as it were, bumping into your predator, or avoid bumping into other cicadas with which you don't want to breed. So primes are an optimal way of minimizing that intersection with those other broods. The reason why they're 13 and 17 is largely to do with their size of the creature and how long they kind of need to be in gestation and development. So there are other primes available, for sure, but as we get too big or too little, there are just kind of more basic biological factors that kick in that prevent it from being, say, name a prime number under 13, 11, right, good. So here we have, again, a mathematical explanation involving number theory about lowest common multiples, which is explaining why the explanations given avoiding predation and maximizing your ability to only procreate with really similar cicadas to yourself, that explains why they're prime. So we've got kind of steps of explanation going. Two examples then, in which we've got some biological phenomena in the world which is being explained by a decent biological explanation, which is being underpinned by a decent bit of maths. So proving this is supposed to be very, very straightforward. That's not supposed to, that it'd take thousands of years to prove that that was the case. Here's something that Alan Baker wants to do with these kind of examples, primarily with the cicada example, but we can talk about either. He gives this argument for thinking that we can draw some interesting conclusions. So, start with this premise. We ought rationally to believe in the existence of any entity that plays an indispensable explanatory role in our best scientific theories. And the idea here is that that's supposed to be quite a good thing to believe, this premise. So, we ought rationally to believe in the existence of entities like electrons, because electrons play an indispensable explanatory role in our best scientific theories. If you want to explain how, you know, computers work or how light moves or whatever, you probably need to make reference to electrons. And your explanation would be less good if you didn't appeal to or invoke the existence of electrons. So given they play this indispensable explanatory role, we really ought to believe in their existence. We ought to say things like, yeah, electrons exist. The unicorns exist. They don't really function in many of my explanatory theories, right? Or any of them, in fact. In fact, there are many things, most things, I think, you know, if I'm trying to explain them, I rarely indispensably depend on unicorns, right? So I don't feel that this commits me to the existence of unicorns, but it does commit me to the existence of, what, electrons or genes. Think about people who thought maybe there weren't such things as genes, right? I don't mean, I mean, units that carry information that can be passed, you know, through a hereditary process, units of information that are, you know, important in that hereditary cycle. People used to think there was something problematic about that notion. And now we think, no, it's good to talk about genes, we should think that genes probably exist. Although in what form they exist, maybe that's up for grabs. So that's the first line here. And then he points out, look, in both of these explanatory things that we've just seen, mathematical objects are playing an indispensable role. So, you put those two claims together, we ought to believe in the existence of any entity, and mathematical objects play that role, any entity that plays that role. So we ought rationally to believe in the existence of mathematical objects. That's his argument, it's in his paper, you can see he does believe it. So that looks like, by looking at current scientific practices, the kind of things that, you know, you might read about in New Scientist, or, you know, some sort of popular science or wherever, what scientists actually really do, not what we kind of fictionalise about what they do. When they're theorising, they appeal to things like atoms, electrons. Maybe we indispensably rely on Higgs bosons. Maybe they're going to play an important explanatory role. In which case, we probably ought to believe that they exist. If we can't explain what's going on inside the Large Hadron Collider without invoking Higgs bosons, then we should probably think that they exist. That's kind of what the first premise says. Then he says, wait a minute, also this theory, in order to be a decent explanation, draws on mathematical objects. Numbers or sets or properties of numbers, those kind of things. So we ought to believe in those mathematical objects. So we have a kind of sciencey looking argument, or an argument that we might otherwise use for normal scientific objects or less recondite scientific objects, for thinking we ought to believe in mathematical objects. What's interesting though is most people agree that if mathematical objects exist, and by mathematical objects I mean things like numbers, sets, functions, those will do. If they exist, they're abstract objects, so they're not concrete objects, they're certainly not physical objects. They don't inhabit this world the way that tables do, or what unicorns don't, or, you know, electrons do, right? They don't have the kind of properties that those things have. And in particular, the general consensus is if mathematical objects exist, or any abstract object exists, it's non-spatio-temporal. It's not, it doesn't exist, as it were, within space and time. It's not subject to change, it's causally inefficacious, so it doesn't bring about any changes. These are sort of eternal, and people call them Platonic entities, right? Which means they sort of inhabit a sort of ghostly other ideal world like Plato's forms do in the Republic and those books by Plato. So what's strange, you might think, about this argument, this enhanced indispensability argument, is that a method that would normally, be totally fine because it gets us the kind of things that we think are pretty, respectable to believe in. At least we grow up in a world in which we think it's acceptable to talk about genes and atoms or genes and electrons. Also can be used to show that we're committed to these Platonic objects. You might think that's strange. One of the reasons you might be thinking it's strange is, how can these mathematical abstracta really play any role in science? How can things like numbers or sets really be doing anything in science, given that they're supposed to be causally inefficacious, and those sort of things? They can't change anything. At least electrons kind of whiz and bang and set things off and that kind of stuff. At least genes do something. But these things are sort of supposed to be causally inefficacious. They're not supposed to do anything. So there's something a little bit strange about it. At least there should be sort of prima facie. So on first glance, it should seem to you a little bit strange that they can be apparently really useful, but at the same time seem to be a kind of inert thing. And I don't mean just like an inert gas. I mean just kind of handicapped, unable to function in the physical world. There's an initial reason for kind of being a little bit reticent about Platonism, right? You might just think, wow, so you've got an argument which looks like a totally sort of normal science, an argument that totally captures what goes on in science, right? This is, that's why we believe in genes, that's why we believe in electrons. But it's getting us to believe in things that seem to be kind of outside of what science does, right? Numbers, those kind of stuff, right? Okay. So let me sort of try and just, really formalise, so I'm just going to swap in words into the new indispensability argument, right? The best explanation of cicadas' prime life cycles is that prime numbers admit of some lowest common multiples. There's a claim about numbers, right? Number theory is supposed to be committed to numbers. Yeah, that seems quite straightforward. It would be odd to question that, at least prima facie. So we all rationally believe in the existence of any entity that plays an indispensable role in these things. Well, look, here we can see that role being played. And here we can see what the commitments are of that number theory, that numbers exist. We ought to rationally be committed to believing in the existence of entities that play this indispensable role. So, given that number theory and numbers do play an indispensable role in our best scientific theories, we ought to believe in numbers. So that's the kind of the argument in a nutshell. And I'm sort of skimming over lots of qualifications that Baker puts in when he talks about this in a later paper, because people have come back to him and said, there are some real problems in how you formulated that, with what how you've turned the explanation going on, those sort of things. So he's got a sort of more nuanced version, but we don't really need that for these purposes. This is just a point being made that numbers play some indispensable role in science and scientific explanation. We should believe in the things that play that role, so we should believe in the existence of numbers. We should be committed to the existence of numbers. So one thing you might think is, if I wanted to show you that numbers existed, there could be loads of different types of ways I could argue for it, and some of them might be just really a priori. I just sit in an armchair, I do what philosophers do, I just think really hard. What exists? What did Kant tell me exists? Well, he's right. So and you could just do that kind of very, like you say, very metaphysical kind of project of ontology. And this, is very different because it takes kind of the business of science quite seriously, and it says, well, that's one way of working out what exists in that heavyweight philosophical metaphysical task, and here's another way. It's just looking at what scientists do and what they say, and they regularly tell us what exists, and we normally believe them, and that seems to be doing pretty well for us. When they say, there's not a bridge there, we would think, well, let's not step out or something. It looks like this normal way of experiencing the world is a good way of working out what exists, and he's just kind of using that and showing, well, that might also get you some of these weird metaphysical objects as well. This is just the same argument again, but this time instead of using the cicadas, using the bees one. It's just running the same argument again. So there's something that we can observe, which is that bees make hexagonal honeycombs, and we can give a kind of biological explanation of that, which is that would be evolutionary, a successful or optimal thing. We can then give a kind of proof of why it's optimal, and that will be committed to numbers. It really does. It really does look like it is, I guess. We ought to believe in the existence of whatever plays that explanatory role, and so numbers do play an explanatory role. So we ought to believe in the existence of abstracta like numbers. So what does it mean to identify an explanation? Some people might think, well, it's just to identify what's causally doing the work. So you haven't explained something until you found the cause. But for interesting reasons, Baker doesn't want to go down that line and criticise the argument on those grounds. He thinks that would be question begging, he thinks. If you just build in a notion of explanation that militates against all abstracta, then, well, you're not going to get very far. He also thinks there are good examples in science, more generally, not involving abstracta, where it's like the notion of explanation going on probably isn't causal. There are other notions of explanation that he could rely upon, which seem also acceptable by scientific lights. Okay, so there's the argument, given twice, just using the two examples. Okay, the way the argument works, and this is brought out nicely by the question that we just used to sort of clarify it. That claim is expressing a principle that people call inference to the best explanation. So that claim is we ought rationally to believe in the existence of whichever plays an explanatory role in our best scientific theories. And this principle, inference to the best explanation, which says you should infer that this thing exists if it plays a role in your best scientific theory. That principle, it seems to be one that scientists use in lots of other cases. And it's something that lots of philosophers would probably want to hang on to, because it makes sense of why we should believe in electrons or why we should believe in genes. So inference to the best explanation looks like it plays a pivotal role in this argument, and it looks like one that we kind of want to hold on to. So saying, well, you know, that's the weakest link, I don't agree that we should believe in these entities just because they play this indispensable role. It means that we might have to sort of start wondering, well, why should I believe in electrons or quarks or bosons? What's permittable about that? Look, I can believe in trees because they're kind of observable, and I can believe in tables because I can see them, but I can't see any of those things. So my reasons for thinking those exist can't just be because I've seen them, right? If seeing is believing or whatever. It can't be that, right? So there must be some other reason why I believe in these, and the reason that seems to be really quite important to a lot of philosophers of science is, well, it's because they play this role in scientific theories. They play this explanatory role. One of the reasons why we should take on the existence of bosons if this big experiment that's going on in CERN works or whatever, is that they would explain why we get the data that we do. As soon as the data starts popping off at that interesting frequency. So what's the best explanation of that? Well, I think it's a Higgs boson, that'll be what it is. And then we should all start believing in them, and we should pretend that we never denied it, and say, I knew they were there all along. What would be nice, though, would be if we could have a principled way of saying, sometimes you can use inference the best explanation, and sometimes you can't. So when it comes to genes and quarks and black holes and electrons, then yeah, inference the best explanation is a really good strategy to use. It's one that most scientists would say, yeah, that's great. Well, I don't know whether scientists would say, I don't think they care about the existence of these things the way that philosophers do, right? So I think they'll probably just say, yeah, whatever. Anyway, it's more data, and then we have to wash our hands and leave or something. But at least what would be nice is to be able to say, in those cases involving, large hadron colliders and stuff, inference the best explanation looks like a decent principle. Good way of working out what exists. But in all those other cases, like maths cases, let's not use inference the best explanation, because then we end up being committed to, mathematical abstracta. And the way that Baker's argument is supposed to work, this enhanced indispensability argument, is supposed to say, you can't have one without the other. You can't, how do you separate these two? How is it that you can rely upon this principle all the time when you're thinking about, atoms and other unobservable things, but you all of a sudden don't want to use it in the case of maths and those kind of unobservable things? It looks like you're just cherry picking which things you want to exist. So instead of working out what exists by following the scientist around and using this principle, you're deciding in advance, oh no, I know what exists. All the stuff that sounds, sciencey enough to me, and none of the stuff that sounds weird, right? That's how I decide what exists. And what I'll do is I'll just say, those are the good cases and those are the bad cases. You can use inference the best explanation there, but you can't use it here. And that just looks like cherry picking. That's like deciding what exists in this kind of top-down, doing your metaphysics first before you've ever listened to a scientist. The sort of thing you might just do from the armchair, and it looks a little bit arbitrary. That would be the concern here. Unless you can come up with a principled way of separating them, unless you can say that, point out what it is that's significant about the maths cases that would stop you from using inference the best explanation. I guess what some people point to is precisely the point that mathematical abstractors just don't seem to do anything. So that would be a reason for saying, well, there's a reason for not using IBE in those cases. So the reason I'm putting parity up there is because the whole point of this argument is you shouldn't go around rejecting the enhanced indispensability argument just because it doesn't give you results that you like, just because it tells you that abstractor exists. Because as you start rejecting parts of it, you start losing results that you do like. One's about whether electrons exist. Okay. Now we're going to talk to you about nominalising really briefly, right? So this is just a quick aside, and it's going to be super quick. So to nominalise a theory is to come up with a way of expressing the same content as that theory, but with being able to sort of jettison your apparent commitment to the objects that it's talking about. So I guess people do this quite a lot. Let me give an example that you might know. Let me think of an example. Oh no, I've given an example. Good, okay, right. So a mathematical nominalist will try and come up with a way to translate away, or get rid of, apparent reference to mathematical objects. And they'll sort of translate them into sort of non-mathematical statements that are not committed to mathematical objects. So let's think of a translation. So here might be something you might say, the number of fingers on my right hand is the same number as the number of fingers on my left hand. It's either 4 or 5, but it's the same number either way. When I say that, it makes me seem as though I'm committed to the existence of numbers. There is a number which is the number which is the number of fingers on my right hand. There is a number which is the number of fingers on my left hand, and it is the same number. When I start talking that way, it sounds, this is a very cheap example, right, but just to get into it, it sounds like I'm apparently committed not only to fingers, but also to numbers. But you might think, well, there's an obvious kind of paraphrase, that's not really how we think these things work, right? Apparently committed to numbers, but we might think, it doesn't really claim about numbers, it's about fingers and what you can do with them. You might say, well, I can kind of express this same content without making any reference to numbers. I can say, when I take my fingers and kind of, line them up, I can do that and it always works, and there are none spare. And when I say none, I don't mean 0, and I don't mean not 1 either, because that sounds like I'm talking about numbers as well. But it looks like it's something that I should be able to do. Think of other paraphrases that exist just more generally, right? So you might think when people apparently say things that commit them to the existence of strange entities, like, well, the average man is 5 foot tall. You might say, well, where is the average man? But obviously they're not talking about a particular man there, right? They're talking about a slightly more complicated function which doesn't really involve any one person being the average man, for example. So we quite often paraphrase away from apparent commitment to certain types of entities. I don't think there is an average man when people say that. I think that they're expressing something slightly more complicated. Nominalists are trying to do that here, mathematical nominalists are trying to do that. They say, imagine there was a sort of paraphrase strategy that I could use, or a sort of translation or something, that would take apparent reference to numbers and say, well, actually that's just something else you can do. Maybe it's an ability. Apparent reference to numbers is actually just about your ability to do a counting operation. And counting is just something you do, like skipping is something you do. There's no mathematical objects involved in skipping, and nor is there in counting. It's just a thing you do, it's an activity. Might be various strategies available there. That's nominalising, right? So this is the kind of the weak argument that I wanted to bring at the end then, right? So this is my argument for a weak conclusion, right? Let's take a thing that's in need of explanation, a thing that we want science to explain. And in philosophy we call that thing an explanandum. It's a Latin word and ends with the word dum. So here's something that we want to explain. Why do bees make hexagonal combs? Or why do cicadas have prime life cycles? We've seen both of those explananda today. The plural of explanandum is explananda. So those are two things that we want explaining by science, right? Or anyway, but we think science is going to be the best explainer of those things, right? Then we've seen some biological theories that aim to explain E, the explanandum. So here are the biological theories that we've seen. And in philosophy we call those explanans, the thing that's doing the explaining. So the done is the thing in need of explanation, the explanans is the thing doing the explaining. So in each case, the explanation, which we're labelling T, is a sort of biological explanation, and it says, so this one explains the top explanandum, and it's the evolutionary optimality of using hexagons. That would explain why bees make hexagonal cones. Similarly, the evolutionary optimality of prime life cycles would explain why cicadas have prime life cycles. So there we've got T in each case explaining E, some biological theory, T explaining some thing that needed explaining, which was E. And then we've also brought in a mathematical explanation. Again, an explanand. Hales's proof of the honeycomb conjecture is itself an explanation of this, of the evolutionary optimality of using hexagons. So something that was previously an explanation, an explanans, is standing now as the explanandum, which is explained by M here. So it's interesting that T can play that role. The biological theory can at once be an explanation, it explains E, but it's also something in need of explanation. Why are hexagons evolutionarily optimal? And then we bring in Hales's proof of the honeycomb conjecture, and then we have an explanation, a mathematical explanation. And similarly, another version of M, but to explain the other one that we were looking at. So those are just supposed to move in parallel, right? So something needs explaining, that's what we're calling E. T is supposed to explain E in each case, and T is a sort of biological theory. That's why I've given it a T for theory. And then each time we've brought in a mathematical explanation to explain T, and that's M in each case. So just get that totally clear. T explains E, M explains T. Right, that's what I've just said. I'm just sort of putting it so you can kind of see it all lining up. And the claim here is that T and M is a better explanation of E than just T by itself. So the biological explanation of why cicadas are doing this crazy thing is an explanation, but a better explanation is one that's also explained by why prime cycles have that feature, and that's done by the number theory, by M. So if we have both T and M, we've got a better explanation of E than if we've just got T. Similarly, you might think Darwin was right when he said, yeah, well, what explains why bees make hexagons is because it's evolutionarily optimal. Well, we made a step forward, an interesting one, an explanatory one, an extra step, when we learned that actually hexagons are the most efficient way to tile a plane. So Hales's proof did do some work. It was extra explanatory. So it's a better explanation than if we just had Darwin's kind of almost like a conjecture of an explanation, but it was just more efficient. This says, we ought to believe in the existence of any entity that plays an indispensable role in our best scientific theories, and here T and M is better than T alone. So we've got a better theory, that conjunction T and M is better. So we should not just believe in the stuff that T is saying, the biological theory, but we should also believe in the stuff that M is saying. So I'm just kind of reiterating the way that the argument worked. We've got a better explanation here. Now imagine there are two competing versions of M. So there's a version of M, which is our mathematical theory, which is committed ontologically to the existence of mathematical objects. And then imagine there's another theory of M, another version of M, which is just a nominalised equivalent. So it seems to sort of say all the same content, but it just, kind of dissolves away its apparent commitment to numbers. So there we have a kind of a nominalised version of M. We've got M, which is the Platonist version, which says, there are numbers and they do all this work. And then we've got the proof that Hale uses, whatever. And then we've got the nominalised version, let's call that NN, and that's the kind of paraphrase strategy which gets rid of that apparent reference to numbers. And so our question then is the conjunction of T with the Platonic mathematical theory better than the theory with the nominalist version of that mathematical theory? Because if it is, then we should really believe in the existence of numbers. But if it's just as good as the nominalised version of maths, then it looks like we could probably dispense with that commitment to numbers. So it's a question here about which does the better explanatory work. Does the Platonist version of that mathematical theory do better explanatory work than the nominalised version of that mathematical theory? And I guess what I'm thinking that I want to say here is there's a reason for thinking the Platonist version does better than the nominalised version, which a Platonist would be very happy about, would commit us to abstracta. They'll say, yeah, it is a better explanation because this nominalised version that you're thinking of doesn't exist. No one's given it. Has anyone actually gone and nominalised the whole of bubble theory or graph theory and the sort of things that Hale is relying upon? I mean, you can barely do it with that crap example using your fingers or that crap example using the average man. Do you really think you can do it, nominalise away all the mathematical content of graph theory or of bubble theory? Probably can't be done. So that's the sort of pessimistic outlook. In which case, we should go for the Platonist version. Yeah, we should just say, it's because numbers really exist. Yeah, okay, we're indispensably committed to them. Given that's just a conjecture, right? So yeah, I agree, no one has made that nominalist paraphrase yet. I think a reason for thinking that the nominalist can kind of fare well here and say, I don't really want to be committed to mathematical abstracta. I don't think that the mathematically loaded version of your theory is better than this possible conjectural nominalised version that I can come up with. And it will be this, right? You think that this sort of chain of explanation bottoms out with the existence of numbers. So you think when we come to try and explain things, the stopping point on that chain of explanation is just that, abstracta exist. So it looks like there's very little more to say about them, so much you can do to abstracta. So you're kind of drawing a line right at this level. Hale's proof is the last thing that we can say about why it is that bees do what they do. But what we saw earlier was something which at one stage is an explanation, an explainer, an explanans, can, in other terms, be seen as an explanandum, something in need of explanation. That happened with those kind of biological explanations. They stood in need of further elucidation, and that's what Hale's proof was supposed to bring. And if you think that chain is actually a virtuous thing, having that kind of continuous chain of explanations, of one thing which explains the next, and that thing itself is in need of explanation, and that thing is itself in need of explanation. If you think that's right, then it seems fairly arbitrary to just stop as soon as you think you've hit some point where you've got mathematical abstracta, and to say, well, I just imagine that you can't go any further, I just imagine it can't be done. So the argument here is essentially one of saying there are reasons to be optimistic, or to at least hope that this nominalising project can be done, even for things like bubble theory, because it looks like a virtue of the way that science works, that each thing that it relies upon, it then goes on to try and explain, and kind of getting further and further into what makes up reality, or what makes up why things do the things they do. There's something disappointing about stopping by saying, numbers did it. That's like you're saying, a wizard did it. You're kind of drawing an end to the line of explanations. It's just magic. It's just those ghostly numbers. That's why. There's my conclusion then. But I think weakly that there are reasons to not feel that the indispensability argument should commit you to the existence of abstracta. Because I think there's a case to be made for thinking that we should keep pushing on with the nominalist project.